Okay, exploring similar polygons. In this section, we want to get a good understanding of what similarity means, how it's different than congruence, and how we can use that to solve for missing measurements. So let's dive right in. First of all, our symbol for similarity is a single tilde, a little bit different. Uh, and we could say that two polygons are similar if their corresponding angles are congruent and their corresponding sides are proportional. So with congruence, we said same shape, same size. With similarity, we're going to say same shape, which means the angles are congruent, but we're going to say proportional size. Size refers to the sides or segments, and they're proportional. One, that means that there's a common scale factor. And two, that means we can use proportions. Now, a proportion is nothing more than a fraction equal to a fraction. A over B equals C over D. And we're going to cross multiply. So sometimes scale factor is obvious and clear. Sometimes it's not. And the best way to do it is using a proportion. So we want to get comfortable with setting up proportions. Proportions can be set up multiple ways. It is all about using the corresponding parts and putting them in corresponding positions in that fraction. If the hypotenuse goes in for A from triangle 1, then maybe it should go in for C in triangle 2. So it's in the numerator of both. We'll look at a few different ways because there are different ways to set up any proportion. So again, similarity means that the angles stay congruent, but the sides are proportional. We can write a similarity statement in corresponding order. So we've been doing corresponding order for a long time. And just a reminder of scale factor from back when we did dilations. Remember, a dilation on the graph makes the image bigger or smaller. So it creates a similar image. So scale factor can be calculated the same way. It is the new measurement over the old measurement. Any scale factor over 1 is an enlargement. Any scale factor between 0 and 1 is a reduction. So we can certainly determine the scale factor, again, the way we have in the past. When it comes to triangles, it is not just the sides that are similar, but our special segments as well. So if we double the size of a triangle, well, we doubled all the sides. Common scale factor, which means we doubled the perimeter. We also doubled the altitude and the length of the median and the length of the mid segment. So the special segments that we spent time learning, they are all affected by the same scale factor as well. And you can see those on the screen. Mid-segment, angle bisector, median, altitude, and perimeter. Any of these can be used in our proportions. Remember, a proportion is a fraction equal to a fraction. So we will need two parts from each triangle. And it might not always be triangles, but I'm using that as the example. We'll need two parts, two segments. Well, these qualify. We can use two sides, or we could use one side and a median, or one side and the perimeter, or the altitude and the perimeter. We can use any of these things in our proportions, and we'll see a few different examples. So let's look at a simple example here. We have two quadrilaterals. These two polygons are similar to each other. We're going to solve for x. We always want to work with the corresponding parts. So for example, here's our x. That x connects two different angles, angle 3 to angle 4. That corresponds to the 12. So those are the corresponding parts of those two polygons. In the second polygon, we have the 6. Well, that corresponds to the 9. So now we know the 4 things that are going to go into the proportion. So now the question becomes setting up that proportion. And there's a few different ways to do it. I'm going to show you a couple different ways. So the first way is we could do, we could do polygon 1 and make a fraction out of that. So I'm just going to go left to right, 9 over 12. Then from polygon 2, we're going to match that, the corresponding parts. So we did 9 over 12. We're going to match that with the corresponding parts. In this case, it would be 6 over x. 6 corresponds with the 9, and the x corresponds with the 12. And of course, we can cross multiply that and solve it. We get 9x equals 72, and x equals 8. So first fraction from the first picture, second fraction from the second picture. The corresponding parts are going across. Across the numerator and across the denominator. Now, of course, we could have flipped those fractions. So if we started out with 12 over 9, we would do it as x over 6. And we get the exact same results. Another way to set up the proportion would be to do polygon 1 over polygon 2. And then make sure the corresponding parts go across the numerators and across the denominators. So for example, I could do something like 9 over 6. Those are the corresponding parts, polygon 1 over polygon 2. I would match that with the other pair of corresponding parts, polygon 1 over polygon 2. And you can see when we cross multiply, we get the same 9x equals 72, and therefore we get the same value of x. And of course, we can flip both of these. 6 over 9, x over 12, doing polygon 2 over polygon 1. So that's 4 different ways to set up the same proportion, get the exact same results. The proportions are all about the consistency in the way we set it up. The fractions can also be reversed. It could have been 12 over x equals 9 over 6. So there's multiple ways to set up proportion. It's about the corresponding parts and put them in corresponding locations of your proportion. So working out another example, we're asked to find xz and yz. We'll do one at a time. So xz, let's give that a variable. So from the second triangle, the bigger triangle, I have x, and the only other thing I know is a 12. So I have to use the x and the 12. I'm going to match that with the corresponding parts from the first triangle. X connecting angle 1 to 2. corresponds to 5. So that's going to go in the numerator. The denominator was 12, so the corresponding part is 3. And of course, we can cross multiply and solve it. Now for yz, we'll give it a different variable, maybe y. And I have to use that side y with another side from that triangle. I could use the 20 or the 12. It doesn't matter, long as I use the corresponding parts from the smaller triangle. So for example, I might do y over 12. The y corresponds to the 4 in the numerator. The 12 corresponds to the 3. And when we cross multiply, we're going to get 16. In this example, the scale factor is easily observable to be 4. 3 times the scale factor equals 12. Or we can say the scale factor equals 12 over 3. So we get a scale factor of 4. 3 times 4 is 12. 4 times 4 would have given us our 16 for y, and 5 times 4 would give us the 20 for x. So sometimes scale factor is easily observable and usable. Sometimes it isn't. Finally, in this question, we are asked to write a similarity statement. So remember, just like congruence, the first triangle you can name however you want. The second triangle has to be in corresponding order. So for example, my first triangle, if I do W, V, U is similar, and I'm going to follow it up with Z, Y, X. Z, Y. Corresponding order. So I went angles 1, 3, 2. I'm going to follow that with 1, 3, 2. We're asked to just complete the similarity statement and determine the scale factor. So LKM to triangle RSQ. And the scale factor, the note says that the statement indicates direction of the dilation. So we're going from LKM to RSQ. So that means this is, this is the old, this is the new. So scale factor equals new over old. Now we can do any pair of sides. It makes no difference because they all use the same scale factor. So for example, I could do 6 over 9, and my scale factor is 2/3. It got smaller, so I expect something between 0 and 1. If I did 8 and 12, this would still reduce to 2/3. So it does not matter what pair of sides. They all will reduce to the same scale factor. It is a common scale factor. Let's look at an example here. We're asked to solve for x and y. So I'm not going to do them both at the same time. I'm going to find the parts that I'm going to use. So x corresponds to the 20. Now, if I'm not going to use the y, then I'm not going to use the 21 either. I have to work with corresponding parts. So if I don't want to use the y, then I have to use the 12, which corresponds to the 18. And we can see we can do something like x over 18 equals 20 over 12. And of course, we can work that out. 12x equals 360, and x equals 30. Now I'm going to go ahead and solve for y. So I'm going to use the y and the 21. So y and 21. And I'm going to match that up with another pair. I could use the 20 and the 30, or I could use the 12 and the 18. It does not matter. Again, this is about setting it up with consistency. So I did triangle 2 over triangle 1 in this example. I'm going to do the same thing using a different pair of corresponding parts. So I might do triangle 2, 12 over triangle 1's 18. And we get y equals 14. Again, multiple ways to set up any proportion. So I did it two different ways in this example. In the first example, fraction 1 from triangle 1, fraction 2 from triangle 2. In the second example, I did each fraction are corresponding parts, and I did triangle 2 over triangle 1, just to show you a variety of ways to set up your proportions. Here we have quadrilaterals, but similar process, similar way of doing it. X corresponds to 8, so I know those are going to work together. So I could even write that already. X pairs with 8 from picture 1 to picture 2. And now I have to find another set of segments where I know the numbers. I don't want any more variables. If there's an X, that's okay, but I don't want a Y. So, for example, I could use the 9 and the 6, or from the left, the 6 and the 4. It doesn't matter. What matters, whether I use that pair or the 9 and the 6, is where I put them in the fraction. Since the left, I did left over right, then I have to do left picture over right picture. And that's going to let me solve. Now I want to go ahead and solve for y. The y gets paired with the 15. The y gets paired with the 15. Those are corresponding parts. Now again, I can do the 4 and the 6 again. But this time I went right over left, so I have to go right over left. This is all about the consistency in the way we do it. And now we can look at our answers and see if our answers are consistent. So we can go on one picture, it goes 6, 9, 12, 15. Go right around that picture from smallest, and it keeps getting bigger. 6, 9, 12, 15. The other picture we should observe the same relationship, 4, 6, 8, 10. So even though the whole shape is smaller, the corresponding parts line up with each other. So we're seeing how to set up proportions multiple different ways. In our example here, notice that we have sides. Well, we have sides and altitudes. Well, we can do side over altitude equals side over altitude. We could do side over side equals altitude over altitude. What we're looking for is consistency in the way we approach it. Either of these are going to give us the exact same results. So let's grab our calculator. We get 17.3x, 24.22. 634. 0.64. I'm sorry, 564. And now we're going to divide. Since we can only be accurate to the tenths, we're going to have to divide here and round. So 36.7. We can only be as accurate as our least accurate number that we're working with. So our least accurate value is to the tenths, then our answer can only be correct to the tenths. In our next example, we're working with sides and medians. So from the first fraction, median over side, and from this, from our first triangle, median over side, from our second triangle, median over side. And of course, we'll cross multiply. So there are multiple ways to set up any proportion. It is more about consistency than anything else. And the last piece here is just, do we have consistent scale factor? Do we have constant scale factors? Or can we set up a proportion to test? So we want to determine if these polygons are similar. And this is going to carry over into the next section of material anyway. It's just an idea to observe it. For example, we might do something like the scale factor new over old, right? So 6 over 5. Is that the same as if we did 4 over 3? And these are not the same. We could set up a proportion. Leg over base equals leg over base, and test that. We can cross multiply. 20 equals 18. That's not right. So these are not similar. Now, we'll get more into this in the next section, but it does relate to the idea of a scale factor that we're working with. In the second example, we can see that the small rectangle became the big rectangle, multiplying by 4. So this one's easily observable. 4 became 16, multiply by 4. 4 became 16, multiply by 4. We got to check all the sides. 6 times 4 is 24. And then at the bottom, 6 times 4 is 24. So all 4 sides have the same scale factor. These are similar. These are definitely similar polygons for that reason. Okay. And we'll get more into testing for similarity in the next section.